welcome you all for an interesting video on digital logic design, where in this video, we are going to concentrate on designing a finite state machine, especially for the overlapping sequence detection using Mealy state machine. As we already know about, the synchronous sequential circuits will change the states for every positive or negative transition of the clock signal based on the input and what type of edge triggered flip-flop that we're going to use for the problem. So this behavior of synchronous sequential circuits, which are represented in a graphical form, is known as the state diagram. And synchronous sequential circuit is also called as a finite state machine if it has a finite number of states. There are two different types of finite state machines and two different types of sequence detection that we can do. In this particular video, we'll be concentrating on the overlapping sequence detection using Mealy finite state machine. Before we proceed with the objective of today's video on overlapping sequence detection using Mealy machine, first let us understand what is non-overlapping sequence detection and overlapping sequence detection using a simple example. So here the input sequence that was transmitted is considered to be 01100101000, and once we know what sequence we have to detect, then based on the transition of the clock signal, we'll be able to identify whether we have received our desired sequence 010. Based on that, the output of the sequence detector is set to be high. In the first case of non-overlapping case, we are going to start finding out the sequence 010 in the input transmitted sequence. So considering that, I start with the first bit that was received in my sequence, which is 0. And then I proceed with the second bit, it is 1. Third bit, when I reach here, it is 1. So therefore, when you have reached the third bit, you just check for the previous bits. When you're in the first bit, you don't have any previous bits, so you don't have to check. When you have reached the second bit, also it is not satisfying your desired sequence, so you have ignored, so you have set your output detector to be 0. When you have reached the third bit, you have previous 2 bits, which is much similar to the number of bits given in the desired sequence. So therefore you check, but that is not my desired sequence because here we have 011, but the expected sequence is 010. So therefore, again, the detector has been set with output to be 0. So as and when you progress for each and every bit, and when you come here at your 7th bit, when you look at here, it will be 010. So when you're at the 7th bit position, your output can be set to be high. Once in the non-overlapping sequence detection protocol, if you have set your output to be high, we will have to start the next detection sequence as a fresh sequence. See, because you will understand when I come here for this 1, I have again set to 0 because when I look back, it is not getting satisfied. I have got 101, but my desired sequence is 010. So I have set my output detector to be 0. But when I come here, the last before bit, it is 0. But when you look at the previous 3 bits, it is 010. Because you are following a non-overlapping sequence detection, you don't have to look for the previous sequence bits before your output to be 1. Which means once you have set your output to be 1 at any point of the sequence detection, you start as a fresh sequence. Which means here I have set the output detector to be 1. So when I reach at this point, I'll look out for my previous bits, but that I will start with a fresh sequence. So I don't have my previous bits, so my output has become 0. Similarly, when I have reached here, the previous bit is only 1. That's why we are not taking these bits. This is not taken in the non-overlapping sequence because once my output detector has set the output to high, I will ignore the previous bits when I'm standing at this particular position. So which means when I stand at this particular position, I look at that I have received only 1 bit. I start every time when the output detector has set high, I will start detecting my sequence as a fresh sequence. So when I come here only, I have reached the 3-bit sequence, but still it is 100, but my desired sequence is 010. So therefore, the output is again said to be 0. But in the case of overlapping sequence, you can look at all the previous sequence. You don't have to start every time when your output detector is set to be high. You don't have to start as a fresh sequence in the case of overlapping detector. So now look at here. So the same, until this we will try to follow the same thing like your non-overlapping sequence detection. So here if you have reached, it is 010. When I come here, though the output detector has set high at this position, I will still look out for my sequence, previous bits in the sequence, because it is an overlapping sequence. Therefore, when I come here, it is 101. 101 is not same as my 010, so I have set as 0. When I come at this position, it is 010, so I am able to detect one more sequence of my desired one. So therefore, the output detector has set to be high. So this is the basic difference between a non-overlapping sequence and an overlapping sequence detection. Now coming to a small brief about the finite state machines. Finite state machines are the heart of most of the digital system design. The basic idea of a finite state machine is to store a sequence of different states, and transition between them also will be stored depending on the value of the inputs and the current state of the machine. And this FSM can be of two types. One is Moore and the Mealy, where Moore sequence, the FSM, will determine the output of the state machine based on the current state variables alone. Whereas in the case of Mealy finite state machine, output can depend on the current state variables and on the input values. And the number of states in a Moore machine will be more than the Mealy state machine. Output in the Moore state machine is placed on the states, and here the output is placed on the transition. And Mealy machine is a bit difficult to design than your Moore machine. So here in Moore machine, the most important thing that we have to understand is the output dependency is only based on the current state variables, whereas the Mealy state machine output depends on the state variables, and which means the current state variables and the input values. Here is a very simple example that I'm going to discuss about the overlapping sequence detector for the sequence 1011. The major purpose of this particular slide is to understand about the state diagram, because state diagram clearly shows the transition of the states from the present state to the next state and the output for a corresponding input. In this diagram, a state is represented by a circle, and the transition between the states is indicated by the detected lines, the arrowed lines connecting the circles. Each circle is a state. Binary number can be represented inside each circle that will identify the state the circle is going to represent. Here I have used the representation of that particular state in the alphabets. The directed lines are also labeled with two binary numbers, which you can see that the two binary numbers are separated by a slash. The input value that causes the state transition is labeled first. The number after the slash symbol gives the output value. So information contained in the state diagram is going to be transformed to a table that you call it as a state table or a state transition table that will give you a clear-cut idea about what is the present state, what is the next state, and the output. So all these things will proceed for a particular design problem. Now here we will first try to understand about the overlapping sequence detection alone. So here, based on the number of bits in the Mealy model, I try to set the number of states here. Okay, so 1011, so I've got 4 bits, so n is equal to 4. I've got 4 states which I have represented as A, B, C, D. Later on, when I discuss for a specific problem, I'll tell you how to set the state variable combinations of A, B, C, and D. So initially, I start with A, which is the first state. So which means I set 0, and I've already told you the binary number which is in front of the slash symbol is nothing but your input. After that is your output. So for the initial state, I assume that my input is 0. output is also 0. So therefore, I stand at the same state. So which is the current state of A. When I have received 0, I am at the same state. Why? Because I am receiving 0 and I am staying at the same state. Because look at the desired sequence that I have to follow. I will move from the present state to the next state only when I have received 1, 0, 1, 1. So the first bit is 1. Therefore, when I have received 0, I am staying at the same state. So the next thing that I should receive is 0. But before that, what will happen if I receive 1? That also we should check. So if I have received 0, I am staying at the same state. Once if I have received 1, I will move to the next state B. Okay, so 1. But my output will still remain to be 0. Only when I have received the complete sequence. That is why I explained the previous slide with a simple example differentiating the overlapping sequence and the non-overlapping sequence detection process. Once I have received complete 1011, only then my output after the slash symbol, the binary number will be set to high. Until then, it will be 0 only. So here I have just received 1, but since I have received my favorite sequence, I am moving forward for the next state. So in B, I have 1. What happens to B if I receive 1 or 0? When I am at this state, what will happen if I receive 0, if I receive 1? If I receive 0 when I am at my B state, I will move forward to the next state. But still my output will be 0 because I have to complete the sequence. Now, when I am at the C state, if I receive 1, I will move forward to D. So I have received 1. I set my output to 0 because I have not completed. But still I can move forward because I am trying to receive 1, 0, 1. Now the last bit in the sequence is 1. So therefore when I am at the present state D, if I am receiving 1, I will move to the next state. But why that next state I am moving to B? So that's the question here. So that we will have to understand with the simple shortcuts. To start with the analysis, first understand till B we have received 1. Till C I have received 1, 0. Till D I will receive 1, not 1. Now we will try to understand because here we have to check what we are going to receive. So when I am at state B, until that I have received 1. So now here I will check. I will go to the next state if I receive 0. And output will be 0 since I have not completed the sequence. Now suppose if I am at the same state B and I am receiving instead of the 0, if I have got 1, what will I do? So now look at here, you should fix here as 1. So now when you have to start your simple shortcuts, you have to read from the LSB position. So now it is here 1. You have to group 3 bits. Since the 3 bits have not been received, you will look out for 2 bits. So when you group 2 bits, it is 1, 1. This 1, 1, you will try to check whether it is matching your first 2 bits of 1, 0, 1, 1. First 2 bits of 1, 0, 1, 1 is 1, 0. Here it is 1, 1. So it is not matching. So I am just going to reduce the number of bits. So I will reduce it to the LSB only. From here only I will have to read. So now I will check whether this 1 is same as the first bit. Yes, it is same. But where it is 1, I have received 1 at B only. So until that, it will stay in the same state. So which means if I have received 0, I will go to next state C. If I have received 1, until which you have received 1, until B only you have received 1. So it will stay in the same state, but the output will still be 0. Similarly, now we will proceed with 1, 0. Until C, I have received 1, 0. Now at C, if I receive 1, it is my desired sequence 1, not 1. So I will move to the next state, that is D. So 1, 0, 1, outputs are 0. But instead of this 1, if I am going to receive a 0, what we are going to do? So now again same thing, read from the LSB. It is 3 bits. it is 100. 100 is not same as my first 3 bits in the sequence 101. It is not same. So now just reduce to 00. 00 is also not same as 10. So this also we will ignore. Now we'll finally have only 1 bit 0. 0 is also not same as the first bit in the desired sequence. So it will completely break the sequence and it will go to the initial state itself. That's why it is going to, if I receive 0, input is 0. My output will be 0. But where I will go, I will know where it is satisfying my desired sequence. So I'll go to the initial state to reset, to restart my sequence. Now I will start with 101 because if I get the desired sequence, I have reached a D. So now from D, if you get 0 or 1, so that analysis we are going to do. So if you are going to get 0, look at here. If you are going to get 0, 1010 is not a desired sequence. So if you get 1010, again start from the LSB. Start reading all the 4 bits. 4 bits it's not matching. So therefore I reduce the number of bits. I read 3 bits. 010 is not same as 101. It is not same. Therefore again I will reduce. When I reduce, it is 10. 10, it is same as my first 2 bits in the desired sequence. Until which state I have received 10? That one I should check now. Until which state I have received 10? Here I have received only 1 in the B state. When I have reached my C state, I have received 10. So therefore, it will go to C state if it has received 0. So when D state is your present state, and if your input is 0, it will go to the C state because you will check for 10. 10, you have reached, you have attained 10 at C. So therefore, it is going to C state with output as 0. Because you have not completed the sequence. When you will complete your sequence, I will complete my sequence. If I receive at D, if I receive 1011, 1. So until 101, you have received, and that's why you are at this state. Now if it is 1, 1011 is much similar to your desired sequence, but where will you go? Where is going to be your next state? So that how will you check? Again, the same protocol that you have to follow. Start all the 4 bits, all 4 bits are same. Okay, but start looking at from the LSB. If you look at that, 1011 is much same, and then you reduce the number of bits and check, it is 011. 011 is not same as, you'll have to write here, 011 is not same as your 101. And then you reduce the number of bits, it is 11. 11 is not same as 10, which is the first 2 bits in the desired sequence. And then you reduce it to only 1. So 1 is much similar to your first 1 in the desired sequence. So therefore, until which state you have received 1? Until which state you have received 1? Until B only I have received 1. Therefore, at D, if I receive 1011, I will go to B. So input is 1. When I am at D as my present state, input is 1. I have completed my sequence, so therefore my output is also 1. But why do I go to B state? I go and check in the previous sequences until which I have received 1. That you should always start reading your desired sequence from the LSB position. Start grouping 4 bits. 4 bits are same as your desired sequence. Then again also you reduce the number of bits and see. It will be 011. 011 does not match the first 3 bits in your sequence, and 11 is also not matching because you're reducing to 2 bits. That is also not matching. When you reach the last bit, it is 1. Therefore, you're going to B. Okay? So that's how, because you should not stop 1011 if you have received. Yes, 1011 I have received. So 1011 and 1011, you should not stop at D itself. You should know, you should complete the sequence detection. The sequence detection gets completed only when you reach B. If you are going to reset and complete the loop to A, it will reset. It will not continue with your sequence detection. So now look at here. If you have reached B, this one only has received 1. This A has not received 1. Okay, so that you should make it sure that you reach to the proper state before your completion of the sequence detection. That's why we reduce till the 1 bit and find out where you should go. Okay. Now, I would like to discuss about the design steps for a Mealy model sequence detection process in the case of overlapping sequence. So first we need to draw the state diagram, construct a state table with state values, excitation table, transition table, and then the K-map simplification procedure, which you're all much familiar, and then finally the logic diagram. So this is how a problem statement will look like, where you have to design a Mealy model sequence detection for an overlapping sequence of 101. So how to start with the state diagram? Here you don't have to understand how this input sequence will be there. Input sequence you don't have to worry. What sequence we should detect? So that is 101. So now how to start? The same procedure, you should try to recollect how we have understood to draw a sequence detection for overlapping sequence of 1011. There we had 4 bits, so therefore I've set 4 states. Here n is equal to 3, therefore I set only 3 states, A, B, C. So now what will happen? We will start with the initial point. A is the initial state, and then I have got B. Until B I will receive 1, until C I will receive 1, 0. That's all. So now we have to check what if we are going to receive the undesired one. If we receive the desired sequence, it's going to move from the present state to the next state. So look at here, A is the initial state. It is 0. Because why we are at the same state? Because 0 is not same as my first bit in this sequence. It is 1. So if it is only 1 in the first one, it will go to the next state. Since it is, we have to start with 0. A is the initial state. 0 is the initial one. So therefore output will be definitely 0, because you know we have to complete the sequence. Only then the output detection will be 1. So now look at here, at A initial state, input is 0, output is 0, because my desired sequence starts with 1. Okay, so now I will move to B. So it is input is 1, output is still 0, because you have not completed the sequence. At B, until B you have received 1. Now at B, if you receive 0, you are going to move to the next state C. But if you receive 1, what you are going to do? It is 1. So now you will start reading from this end, from the LSB position. It is 1, 1, but your desired sequence is 101. So we will try to check the first 2 bits. First 2 bits in your desired sequence is 1, 0. 1, 0 is not same as your 1, 1. So we will reduce to 1 bit. 1 bit is nothing but 1. 1 is same as your first bit in the desired sequence 101. So therefore 1 until which you have received 1. Until B you have received 1. So you'll have to stay at the same state B. Okay, until this state B only you have received 1. So I stay at the same state, output is 0. And then if I have received 0, 1, 0, I will move to the next state. So at C I have received 1, 0. Now at C, if I am going to receive the input as 1, it will move where, and it will move where when I have received 0. So that's the 2 case that we need to discuss. It's very simple, because we have seen for 4-bit sequence itself. Now it is very simple. First we'll go with the desired sequence and complete the diagram. If I have received 101, I'll check these 3 bits. 3 bits are same as my desired sequence 101. So I will, if it is same also, we have to reduce the number of bits and check where I should stop. So I will reduce it to 0, 1. 0, 1, here it is 1, 0. In a desired sequence, 0, 1 is in the received sequence. So it is 0, 1, 1, 0. It is not same. Then I will reduce it to 1. If I reduce it to 1, it is 1 in your desired sequence, and it is 1 here. So it is same. Until which state you have received 1? Until this B state. So until this B only you have received your 1. So therefore C is moving here. You can see here C is moving to B to complete its state. when it is 1, and the output is also 1 because you have completed the sequence. Now if you are going to receive 1 0 at the C state, if you are going to be, and if you are going to receive 0, where you have to go. Look at the 3 bits. 3 bits 1 0 0 101 is not same as 100, and then reduce the number of bits to 2. So here it is 1 0, here it is 0 0. When you compare these two, that is also not same. When you reduce to 0, this is 1, this will be 0. That time it's not same. Therefore, it will break the sequence detection and it will go to A, initial state, because it is 0 and the first sequence in the desired one is 1. So it will reset its sequence detection. It will move to the initial state. So therefore, input is 0, output is also 0. Now, once the state diagram is complete, we have to move ahead with the construction of state table. You had only 3 states. Present states can be A, B, and C. And for each and every state, since you have received 2 inputs, either 0 or 1, though the desired sequence was something, we have to always check for the other possibility also. If it is your undesired 1 or 0 also, we have to know where you should go to the next state. And what is your output? Output will definitely be 1 at the last one, because you have to complete your sequence detection. Until that, output is going to be 0. Now, how do you construct the state table? It is completely a translation of your state diagram. So look at here. A is in your present state. It was 0. If the input was 0, output is 0. You have retained in the same state. So just look at the state diagram and try to construct your state table. And if your present state is A and input is 1, definitely it's a desired one, because we were doing the sequence detection protocol for 101. So therefore, we have moved to the next state, which is B. When you have received 0, it is a desired one, therefore you move to the next state. And at C, what has happened? If you have received 0, you have reset. You have received 1, you can look at the state diagram, you move to B. Similarly, at B, where if you have received the undesired one, you were staying at the same state. Okay. See, you should not think like if you have received as undesired, because at A, undesired was coming, I have retained at my same state. That's not the case. You can't apply the same rule for all the things. You look at here, at A, you have received your undesired 0, you stayed at the same state. For B also, if you have received the undesired 1, you stayed at the same state. But for C, you are going to complete the sequence. So you have to check for both the possibilities. When you are coming for the last state, don't think that if it is an undesired one, you will stay at the same state. Look at here. It can be at that also. But since for this particular example, if you are going to receive 1 to complete the sequence, you have to go to B, because you are checking until which state you have received 1. So that's why your output is also 1 here. But if you are going to receive 0 as 100, you will reset to A. This is in the case of overlapping sequence detection using Mealy model. Your Mealy model the output is dependent on the state variables, present state variables, and also on the inputs. So that you should also make it clear. For state C, when the input is 1, it moves to state B and produce the output as 1. For all other cases, the output will remain 0, because you have not completed the sequence detection. You can see here, you will have to construct the same state table with state values. Because in the previous one, I have written the present state as A, B, and C. Next state is A, B, C. Based on the inputs that you have received, you have changed your next state. So now you are just expanding A as 00, B as 01, C as 10. The same norms that we will try to follow. Okay, like if it is a 2-bit, how you will represent 2 to the power 2, you will have 4 states. Since out of 4 states, we are designing a finite state machine, we will fix only the finite number of states required. Here I require only 3 states, so it is A, B, and C. A is 00, B is 01, C is 10. This is for Mealy model. Similarly, all your next state variables are also redefined with their state values. And the excitation table is my 4th step. That we know because we are going to design the Mealy model sequence detection using a simple D flip-flop. This is your present state and next state and the output D. D is just a delay flip-flop. So the same state of your next state output will be propagated to your output stage of the D flip-flop. So now this is your state transition table. In the case of counter designs, you will check the next state output and you will design the flip-flop inputs based on the excitation table of the selected flip-flop. Same here. You just understand the number of flip-flops required for the design is calculated based on the number of states. The K state is 3, but we need 2 flip-flop for the design. So it is 2 to the power 2, 4. Okay. So now look at here. Though you have got 4 states, we just design a finite state machine. Therefore, we have taken only a finite number of states A, B, and C, only 3 states. So now look at here. You will have to understand the flip-flop inputs. Okay. Flip-flop inputs, we need 2 flip-flop for the design because it is 2 to the power 2, 4 states. Though you have taken only a finite number of states, we can't take the flip-flop number of flip-flops in a lethargic way. We have to just consider how many number of maximum states. So that protocol we will try to follow. 2 to the power n number of flip-flops will require. For a D flip-flop, you will require 1 input, 1 output. Output you know. Okay. But what is your inputs for the D flip-flops D1 and D0? Because you will require 2 flip-flops. So for the D1 and D0 to fill the flip-flop inputs, you will check for the next state. Q1, Q0 is 0, 0. The same thing. Whatever that is there in Q1 is going to be there in your D1. Okay, flip-flop inputs, no. So input, what input you're going to give, the same only will be reflected in your output. Because it is a state transition table. It's not your excitation table. State transition table, you will fill the flip-flop inputs from the next state output. You will have to check your excitation table also so that you know what output you have got. Based on that, you will fix your flip-flop inputs. Since it is a delay flip-flop, whatever that was there in the input only would have propagated to your output. So the same thing we are trying to fill up. As like your counterpart design, we will try to do the K-map simplification procedure for driving expressions. The driving expressions are nothing but your flip-flop Boolean expressions, flip-flop inputs. Inputs are nothing but D1, D0. Your output, Z also we need to check. So in K-map, we must assume the don't care values for the remaining unknown states. Whatever states that we know, only that we will proceed because you know about 0, 0, 0, 1, 1, 0, you know. Since we are dealing with finite number of states, we have not taken 1, 1. So that will automatically become X. Okay, so in this case, 1, 1 state is an unknown state and its output will be don't care irrespective of whether your input is going to be either 0 or 1. So you will take Q1, Q0, X and derive what is D1, what is D0 and what is Z. So do the grouping as per the K-map simplification procedures and find out the expressions for D1, D0 and Z and then bring it into your logic diagram. So after simplification using the K-map procedure, we understand that D1 is Q0 into X bar, D0 is X, Z is Q and X accordingly. So you will require 2 AND gates. So here is one AND gate, the other AND gate. X bar, you can take it through a simple NOT gate. And then since we are dealing only with simple D flip-flops, D1 is your input, Q1 is your output. We ignore the complementary outputs, but still we try to indicate in the flip-flop design. And since we are dealing with synchronous sequential circuits, clock has been fed to both the D flip-flops at the same time. And this is your output, is it? Hope you all have understood about the overlapping sequence detection design of a finite state machine using Mealy model. So this complete procedure on how to design an overlapping sequence detector was discussed starting from the state diagram. Even before that, we have understood what is the overlapping sequence detection with the given input sequence and the desired sequence for both the cases. In case of overlapping and non-overlapping cases was discussed. And then we have taken a simple 4-bit example of 1011 and we understood about how to set the state diagram because that is the initial point that we fix the state diagram and then we proceed with the other steps in the construction of state table, state table with state values, excitation table determination, and then the final construction of state transition table for filling up the flip-flop inputs, and then the came-up simplification procedure for obtaining the driving equations, which means your flip-flop inputs and the output, final output Z, and then all these things were integrated into your final logic diagram. Meet you all with another interesting video. Until then, stay safe. Thank you all for watching this video through Electronics Insight channel.